They told you a lie in school, a very convenient lie. They drew a little nucleus in the middle and tiny electrons circling around it like planets around the sun. Nice, neat, comfortable. It looked like a miniature solar system. You nodded. It made sense. It's wrong, completely wrong. If electrons actually orbited the nucleus like planets, atoms would collapse in a fraction of a second. The electron, being an accelerating charge, would radiate energy continuously. It would spiral inward and crash into the nucleus. Matter wouldn't exist. You wouldn't exist. This conversation wouldn't exist. And yet, atoms are stable. So something very strange must be happening. The electron is not a tiny marble flying in circles. It doesn't travel on a neat track. It doesn't have a little orbit you could draw with a pencil. In fact, asking where is the electron right now, in the classical sense, is already the wrong question. Electrons do not move like planets. They behave like something far more unsettling, something that forces us to abandon the very picture our intuition demands. And once you understand why, you'll realize the atom is not a tiny solar system. It's something far stranger. All right, a nucleus in the center, electrons orbiting around it like planets around the sun. It's a beautiful picture, and it's completely wrong. Now, don't misunderstand me. It's useful as a first story. But if you take it literally, the universe falls apart. Here's the problem. An electron is an electric charge. And whenever a charged particle accelerates, and circular motion is acceleration, it must radiate energy. That's not speculation. That's Maxwell's equations. Solid, tested, classical physics. So if an electron were really orbiting like a planet, it would continuously lose energy as electromagnetic radiation. And what happens when something in orbit loses energy? It spirals inward, fast. Calculations show that a classical electron orbiting a nucleus would crash into it in about 10, in sus, 11, 10, nus 11 seconds. That's 10 billionths of a second. Atoms would be catastrophically unstable. Matter would not survive long enough to build chemistry. Chemistry would not survive long enough to build biology. You would not survive long enough to ask the question. So the first shocking fact is this. If electrons behaved like planets, nothing would exist. The failure of classical thinking. Physicists at the end of the 19th century knew this was a disaster. They had Maxwell's equations. They trusted them. They had Newton's laws. They trusted those too. But when they tried to apply classical physics to atoms, everything exploded mathematically. Electrons radiate, energy drains, orbits collapse. The model destroyed itself. So something had to give. And what gave was the idea that electrons move in definite classical paths. The first clue, discrete spectra. Here's another piece of the puzzle. When atoms emit light, they don't emit a continuous smear of colors. They emit very specific, sharp lines, precise frequencies. If electrons were orbiting freely, losing energy continuously, you would expect a continuous spectrum of radiation. But that's not what nature does. Nature gives you lines. Sharp, clean, quantized. It was as if the atom were saying, you may not move smoothly here. That was the first whisper of quantum mechanics. Bohr's temporary rescue. Then Niels Bohr came along with a strange idea. He said, what if electrons can orbit but only in certain allowed orbits? And what if, while in those special orbits, they do not radiate energy? It was an outrageous proposal. It contradicted classical electromagnetism, but it worked. Bohr's model predicted the hydrogen spectrum perfectly. Physicists celebrated, but they knew it was a patch, because Bohr had simply declared that electrons wouldn't radiate in certain orbits without explaining why. It was like saying, the rules stop applying here. That's not satisfying. The deeper problem, even Bohr's quantized orbits still imagined electrons as little objects flying around, and that picture kept breaking. It couldn't explain more complicated atoms. It couldn't explain fine details of spectra. It couldn't explain chemical bonding properly. The cracks kept spreading. So physicists had to confront something more radical. Maybe the electron isn't a little ball following a path at all. Maybe the question, what path is it taking, is already wrong. What if the electron does not have a precise trajectory? What if there is no little track around the nucleus? What if the atom is not a miniature solar system, but something that has no classical analogy whatsoever? This is the point where physics stops being comfortable, because now we are not adjusting the picture. We are replacing it. The first hint of the truth. When Schrödinger wrote down his famous equation, something extraordinary happened. The electron stopped being described as a particle in orbit. It became described by a wave function, not a wave in space like water. A wave of probability. The electron wasn't somewhere moving. It was described by a spread-out mathematical object encoding where it might be found. No little planet, no circular path, just a distribution. And that distribution does not radiate energy the way a classical orbit would. The collapse problem vanishes. Stability returns. But at a price, to save the atom, physics had to abandon the idea that electrons have definite classical motion inside atoms. They do not orbit like planets. They occupy quantum states, stable, standing wave patterns around the nucleus. These are not paths. They are solutions to an equation, and that shift from orbit to state is the key. So now we've destroyed the planetary myth. But we haven't yet answered the deeper question. If electrons don't orbit, what are they actually doing? Are they moving at all? Are they smeared clouds? Are they waves? Are they particles? If electrons were tiny balls orbiting like planets, atoms would collapse. So we replaced the picture, but we didn't replace it with another little picture. We replaced it with mathematics. And that mathematics tells a very strange story. The Schrödinger equation changes everything. In classical mechanics, you describe a particle by its position and velocity. That's enough. Give me where it is and how fast it's moving, and I can predict its future. But quantum mechanics says that description is incomplete. Instead, we describe an electron by something called a wave function. The wave function does not tell you where the electron is. It tells you the probability of finding it somewhere if you look. That's a different kind of statement. It's not ignorance about a hidden trajectory. It's the most complete description nature allows. The atom is a standing wave. When you solve Schrödinger's equation for hydrogen, you don't get circular orbits. You get standing waves, patterns in space, where the wave function has certain shapes. These shapes are called orbitals. And here's the crucial point. An orbital is not a path. It is a probability distribution. It tells you where you're likely to detect the electron, not where it is flying around. No radiation, because no orbit. Remember the collapse problem? In classical physics, a charged particle in circular motion radiates energy. But in quantum mechanics, the electron in a stationary orbital is not accelerating along a path. It's in an energy eigenstate. A stable solution of the equation. There is no classical acceleration. So there is no radiation. The catastrophe disappears, not because we tweaked the orbit, but because there is no orbit at all. What does the electron actually do? This is where people become uneasy. They ask, okay, but what is the electron really doing in between measurements? And the honest answer is, it is evolving according to the Schrödinger equation. That's it. There is no little marble flying in circles. There is no hidden track. There is only the smooth evolution of a wave function in time. And that wave function doesn't behave like a planet. It behaves like a wave pattern constrained by the electric field of the nucleus. The shape of the atom, if you've seen pictures of atomic orbitals, those strange lobes and clouds, you've seen this mathematics visualized. The s orbital is spherical. The p orbitals have dumbbell shapes. The d orbitals look like bizarre cloverleaf structures. These shapes are not artistic decoration. They are solutions to the equation. They arise because only certain wave patterns can exist stably around the nucleus, like vibrations on a drumhead. Not like planets in orbit. Why the planet picture persists. So why do textbooks keep drawing little circular orbits? Because it's simple. And because at a very rough level, electrons do have angular momentum. There is a quantity in quantum mechanics that resembles orbital motion. But resemblance is not identity. The electron has angular momentum without following a circular path. That sentence should bother you. It means our classical categories are failing. The deeper disturbance. Here's the truly unsettling part. If you try to force the electron into a definite position to pin it down, you disturb its momentum. If you try to define its momentum precisely, its position becomes uncertain. This is not a measurement error. It's the structure of reality. Heisenberg's uncertainty principle is not a limitation of instruments. It's a statement about what can exist simultaneously, and that destroys the idea of a precise orbit permanently. You cannot have a well-defined path. Nature forbids it. The electron is not somewhere. When people imagine an electron cloud, they often think, oh, it's smeared out like a mist. That's not quite right either. The electron is not a fuzzy blob, physically spread out like smoke. The wave function is not a material cloud. It is a mathematical object that encodes probabilities. When you measure the electron, you find it at a specific location, but between measurements, asking where it really is the wrong question. It doesn't have a classical location. The end of the solar system analogy. At this point, the planetary model is beyond repair. There is no circular trajectory, no smooth path, no little planet. There is a quantized energy state described by a wave equation, stable because it's a standing wave, not because it's orbiting. So now we've replaced orbit with wave function, but this creates a new question. If the electron is described by a spread out probability wave, why do we always detect it as a localized particle? Why don't we see smeared electrons in detectors? We replaced the tiny orbiting marble with a wave function, a mathematical object spread out in space. But here's the immediate objection. If it's a wave, why do we always detect it as a little dot? When an electron hits a screen, it doesn't smear across the surface. It makes a single, sharp click, a single spot, very particle-like. So which is it, wave or particle? And the honest answer is, that question is already wrong. The double-slit shock. Let's look at the experiment that forced physics to abandon common sense. Send electrons one at a time toward two narrow slits. If electrons were little particles, each one would go through either the left slit or the right slit. You would expect two piles forming on the screen, but that's not what happens. Over time, an interference pattern appears. Bright and dark fringes exactly what you'd expect from waves. And remember, we're sending them one at a time. Each electron hits the screen as a single dot. But the pattern of many dots builds up like a wave interference pattern. So each electron behaves like a wave while traveling and like a particle when detected. That is not a metaphor. That is what the experiment shows. When the electron is in flight, its wave function spreads out. It explores both slits simultaneously. But when you detect it, you find it in one place. The wave function collapses to a single outcome. Now here's the uncomfortable truth. Quantum mechanics tells you how the wave function evolves smoothly over time. It does not clearly tell you how or why collapse happens. That's not mysticism. That's the formal structure of the theory. The collapse is a rule about measurement outcomes. It is not described by the same equation that governs the wave's evolution. And that tension is still debated today. Why you can't force it to be a planet. Let's say you stubbornly insist the electron must really be going through one slit or the other. Fine. Then measure which slit it goes through. The interference pattern disappears. The act of measuring which path destroys the wave-like behavior. The electron now behaves like a particle. This is not because we're clumsy. It's because gaining path information eliminates the superposition. The wave function adjusts accordingly. Nature refuses to let you keep both pictures at once. Complementarity, the rule you can't escape. Bohr called this complementarity. You can design an experiment to reveal wave-like behavior, or you can design an experiment to reveal particle-like behavior, but you cannot reveal both simultaneously. Not because we lack cleverness, because the structure of quantum mechanics forbids it. So asking whether the electron really is a wave or a particle is like asking whether something is really north or east. Those are coordinate choices, not identities. The planet analogy finally dies. Now think back to the solar system picture. Planets follow definite trajectories. You can imagine them at precise locations at every moment. That concept requires a definite position, a definite momentum, a continuous path. Quantum mechanics denies you all three. The electron does not trace a path around the nucleus. It occupies a stationary wave state. When measured, it appears at a specific point. Between measurements, it evolves as a probability amplitude. There is no classical orbit hiding underneath. Why this is not just philosophy. This is not philosophical wordplay. If electrons really had classical trajectories inside atoms, they would radiate energy. They would spiral inward. The atom would collapse. The wave description is not optional. It is required for stability. The atom exists because the electron is not orbiting like a planet. The hardest part to accept, the deepest discomfort comes from this. You cannot visualize what the electron is doing in classical terms. And that's okay. Physics is not obligated to match your imagination. The mathematics works. The predictions match experiments with extraordinary precision. If your mental picture fails, it is the picture that must change, not nature. The quiet shift. So now the old model is gone. No little planets, no neat circular paths. Instead, a wave function describing probabilities, quantized energy levels, uncertainty built into structure, measurement revealing localized outcomes. The atom is not a miniature solar system. It is a standing quantum wave bound by electric attraction. But this leaves one more unsettling question. If electrons do not orbit like planets, and they are described by spread out wave functions, what keeps them bound to the nucleus at all? Why don't they simply drift away? No little marble circling, no tiny orbit, no path. So why doesn't the electron just drift away? Why doesn't the wave function spread out into empty space? After all, waves usually disperse. Here's the key. The electron in an atom is not free. It exists inside an electric potential. The electric attraction is real. The nucleus is positively charged. The electron is negatively charged. That attraction is very real. But the way the electron responds to it is not classical. In classical physics, attraction would produce acceleration and orbit. In quantum mechanics, attraction shapes the allowed wave patterns. That's the difference. The electron is a bound wave. When you solve Schrödinger's equation with the Coulomb potential, the electric attraction between electron and nucleus, you find something remarkable. Only certain wave patterns are stable. Only certain energies are allowed. These are called bound states. They are not trajectories. They are standing waves confined by the potential well of the nucleus. Think of a violin string. It doesn't vibrate at just any frequency. Only certain modes are allowed. Similarly, the electron's wave function can only exist in certain quantized states around the nucleus. That's what keeps it bound, why it doesn't fall in. Now here's the subtle part. In classical physics, attraction pulls the electron inward. So why doesn't the electron collapse into the nucleus? Because squeezing the electron into a smaller region increases its momentum uncertainty, and increasing momentum uncertainty increases kinetic energy. That's Heisenberg's uncertainty principle at work. If you try to localize the electron very tightly near the nucleus, the wave function becomes sharply confined. That sharp confinement means large momentum spread. Large momentum spread means large kinetic energy. So there's a balance. Electric attraction pulls inward. Quantum uncertainty pushes outward. The stable atomic radius is where those two effects balance. No orbit required. Stability from mathematics, not motion. The hydrogen atom's ground state is simply the lowest energy solution of Schrödinger's equation. It's not a tiny circle. It's a spherical probability distribution. It doesn't radiate because it's already in a stationary energy state. There's nowhere lower to go without violating uncertainty constraints. The stability of matter comes from this quantized structure, not from little planets circling, angular momentum without orbits. Now here's a detail that confuses everyone. Atomic states have angular momentum. We even label them with quantum numbers that resemble orbital motion. But angular momentum in quantum mechanics is not literally the motion of a particle along a path. It's a property of the wave function's symmetry. The electron can have angular momentum even though it is not tracing a circle. That's not poetic language. That's mathematics. Why chemistry works. Chemical bonding depends on these quantized orbitals. Electrons occupy allowed energy states around nuclei. When atoms approach each other, their wave functions overlap. New standing wave patterns form. Those patterns determine molecular structure. If electrons were little orbiting planets, chemical bonding would look completely different. Quantum wave behavior is not a complication. It is the foundation of chemistry. The planet analogy finally dies. So let's gather the pieces. Electrons are not tiny marbles. They do not trace circular paths. They do not radiate continuously. They occupy quantized standing wave states. Stability comes from uncertainty, balancing attraction. The atom is not a miniature solar system. It is a quantum resonator. Here's the part that really unsettles people. The electron in its ground state is not moving around in the classical sense at all. It is in a stationary quantum state. That doesn't mean it's frozen. It means the probability distribution is stable in time. There is no classical motion to visualize. If you insist on asking where is the electron right now, you are asking a question quantum mechanics refuses to answer classic. Now there's only one final question left. If electrons don't orbit like planets, if their wave functions in quantized states, if stability comes from uncertainty, why does the solar system analogy work at all at larger scales? Why do planets orbit perfectly fine while electrons do not? Fine, electrons are weird, but planets orbit the sun perfectly well. Why doesn't the same logic apply? Good question. The answer is scale, but not in the way people usually think. Classical motion emerges from quantum rules. Planets are also quantum objects. Every atom in them obeys quantum mechanics. But when you combine an enormous number of particles, trillions upon trillions, something special happens. Quantum effects average out. Uncertainties become negligible. Wave behavior becomes invisible. The mathematics of quantum mechanics reduces smoothly to classical mechanics when systems are large and decohered. This is not a guess. It's a theorem. Why radiation isn't a problem for planets. In electromagnetism, accelerating charges radiate. Planets are mostly electrically neutral. They don't radiate energy by orbiting the sun because gravity, not electric charge, governs their motion. And gravitational radiation exists, but it is unbelievably weak at planetary scales. So planets can orbit for billions of years without collapsing. Electrons can't behave classically because they are charged particles in a strong electric field. Planets don't face that constraint. Why orbits work at large scales for a planet? Position can be known very precisely. Momentum uncertainty is negligible. Quantum wavelength is absurdly tiny. The wave nature of a planet is practically undetectable. Its de Broglie wavelength is smaller than an atomic nucleus. So classical trajectories become an excellent approximation. For an electron, the wavelength is comparable to the size of the atom. Uncertainty is fundamental. Wave behavior dominates, so classical paths disappear. Where intuition breaks, here's the deep lesson. Classical physics is not wrong. It is incomplete. It works beautifully when systems are large, decoherence is strong, quantum phases are irrelevant. But when you shrink down to atomic scales, the classical approximation collapses, and the solar system analogy collapses with it. The final picture of the atom. So what is the atom really? It is not a miniature planetary system. It is a positively charged nucleus surrounded by quantized standing wave states, governed by the Schrödinger equation, stabilized by the uncertainty principle. Electrons do not orbit. They occupy allowed quantum states. When measured, they appear as localized particles. Between measurements, they evolve as wave functions. That's the complete story, the real shock. The shocking part is not that electrons are strange. The shocking part is that the solar system picture survives in our minds at all. We cling to it because we want nature to look familiar. But nature is under no obligation to match our imagination. Electrons don't orbit like planets because they are not tiny planets. They are quantum entities described by probability amplitudes. And the stability of everything, every molecule, every object, every living cell depends on that fact. If electrons truly orbited like planets, the universe would collapse in a flash. Matter exists because they don't. The quiet ending, so the next time you see a textbook picture of little circles around a nucleus, remember that drawing is a crutch, a helpful lie, a training wheel. Reality is deeper, stranger, and far more elegant. Planets orbit because classical mechanics is a good approximation at large scales. Electrons do not orbit because quantum mechanics is the real rulebook. And the atom is not a solar system. It is a standing quantum wave, stable, quantized, and beautifully non-classical.